Science 10, Lesson 14, Reaction Rates and the Collision Theory. If reacting molecules do not collide with enough energy, the reaction will not progress. They'll just bounce off of each other. If they're moving fast enough that they could react, but miss each other, well, obviously they can't react. So for a reaction to take place, the molecules must be traveling fast enough to react and effectively collide with one another. This is the basis of the collision theory. Molecules must effectively collide with enough energy for a reaction to take place. Underline effectively collide and enough energy. Those are the two things you have to remember when it comes to the collision theory. Those two conditions must be met in order for a reaction to take place. Factor 1, concentration. In order for a reaction to take place, the reacting molecules must come into contact. By increasing the concentration of reacting species, we increase the number of collisions between reacting molecules, thus increasing the speed of the reaction. Which makes sense. The more molecules that we have present, the more likely they're going to bump into each other. So if we have a low concentration, there will be few collisions. But if I have a high concentration, there will be many more collisions. Factor 2, temperature. The warmer the reactants, the faster individual particles are traveling, the more energy with which they collide. Recall that temperature is a measure of the average kinetic energy of the molecules. So let's liken this to a test in class. Let's say the average was 70%. Well, there's a chance that someone may have got 0%. There's some kids that may not have passed. Most kids, if the average is 70, probably sat around a 60%. And this is the 80% mark. So some kids will have gotten an A on the test. Now let's say the class average is 75%. Well, the curve looks a little different. There's still the chance that someone may have got 0%, but when we look at that 80% line, we have more kids who received an A on the test. Now, if we liken this now to molecules, we have 70 degrees and 75 degrees. When we warm up the molecules, we wind up with the curve flattening out. So at 70 degrees, this is our threshold. Anything to the left is not moving fast enough to cause a reaction if the molecules collide. The right side of that line are the molecules that are traveling fast enough that they could react. And if we look at 75 degrees, we wind up with more molecules now on the right-hand side of that threshold line, so we have a better chance of a reaction taking place because the average molecules are traveling faster, which means there will be more molecules present traveling fast enough for a reaction to take place. A general rule of thumb states that a 10 degrees change in temperature relates to a doubling in the reaction rate. So if I added heat to this beaker that contains my reactants and I warmed it up all the way to 15 degrees Celsius, that means I've increased the temperature by 10 degrees Celsius. The speed of reaction will be doubled. So at 15 degrees Celsius, the reaction would go twice as fast as it would have gone at 5 degrees Celsius. But I'm still heating this thing. And I'm bringing it up now to 25 degrees Celsius, which is an increase of 20 degrees. Speed of reaction has to double again, so the reaction will now go 4 times faster than it would have at 5 degrees Celsius. But it's still heating. It's going up to 35 now. And at 35, that's an increase of 30 degrees, which means the speed of reaction has doubled again. It's now going to go 8 times faster than it would have at 5 degrees Celsius. But it's still getting hotter. The temperature is now 45 degrees Celsius. The temperature is up 40 degrees from where it was. The speed of reaction will have to double yet again. So at 45 degrees Celsius, the reaction should take place 16 times faster than it would have taken place when it was at 5 degrees Celsius. Factor 3, surface area. A solid chunk of substance can only react on the surface. The internal atoms are not exposed, and thus they cannot react. In order to speed up the reaction, the solid chunk of reactant must be crushed so all the atoms are exposed. If I was reacting vinegar with baking soda and the baking soda was in large clumps, I would put it into a mortar and pestle and crush it up as fine as I possibly could. That way, when it gets mixed with the vinegar, all the baking soda will be able to react and the reaction will go faster. Factor 4, molecular shape. When oxygen reacts, it doesn't matter which angle the oxygen is hit because the entire molecule is reactive. A larger molecule may have a harder time reacting because it may only have a small reactive site. When a collision occurs, the reactants may collide, but not at the reactive sites. Therefore, no reaction takes place. Let's look at decanol. And if the only part on the entire molecule that's reactive in this particular reaction is the alcohol, that means that when the molecules who want to react hit this molecule, they may not hit the OH, which means it takes longer for the reaction to take place. It has to wait for the molecules to actually hit the OH site. It is also possible, since the molecules can twist and turn, that the unreactive part of the molecule folds over and guards the reactive site, thus further hindering the reaction. In this case, switching to methanol would make a faster reaction, but it would not make the reaction faster. Huh? Well, if we change the reactant to methanol, we are not increasing the speed of the reaction. We are conducting a completely different reaction. Factor 5, catalysts. A catalyst is something added to speed up a reaction, but is present in the same molecular state after the reaction as it was before the reaction. So it's not like gasoline. Gasoline can speed up a fire, but after the fire dies out, you can't get the gas back. So it is not consumed or destroyed. What the catalyst does is lower the activation energy, lessening the obstacle reactants face on their way to becoming products. Remember, we said when the molecules hit, they have to hit with enough energy that the reaction will take place. So this is called a reaction rate diagram. And we're looking at a non-catalyzed path. So this is just a regular reaction. And if the two molecules coming in don't have enough energy to react, then they just roll back and they remain reactants. The reaction has not progressed. But if I have a catalyst, it makes it easier to get from point A to point B. So those same reactants coming in at the speed that they were not successful at before, now that they have a catalyzed path they can follow, the reaction can take place and they've now turned into products. Enzymes are protein catalysts constructed by all living things to create specific required materials which are highly improbable of forming without the aid of an enzyme. What we're talking about are the things in your body, called enzymes, that take the materials we ingest and break them down so that our body can use those nutrients. Digestive enzymes are mostly produced in the pancreas, stomach, and small intestine, but even the glands that produce saliva in your mouth make digestive enzymes to start breaking down food molecules while you're still chewing. Inhibitors are used to slow down a reaction. They do not increase the activation energy, but rather tie up reactants so the reaction cannot progress. Inhibitors are often used as preservatives in foods and medical drugs, so that the drugs will last longer and your food won't spoil as fast. So let's get into this reaction rates lab. The purpose: construct a lab to test the effects of temperature and concentration on the rate of reaction. Our hypothesis. The hypothesis makes an educated guess as to what the results might be, and it has to be related to the purpose that we just wrote. Writing the hypothesis can be quite difficult and may require you to reflect back on information from past classes or probably today you're going to have to reflect back on what we just talked about. So we are going to test temperature. So our hypothesis will read something along the lines of, if the temperature of the reactants is increased, the speed of the reaction will, you're not going to write change. You have to be more specific than that. We have three options here. The speed of the reaction will either increase, decrease, or not change. You're going to have to select one of those answers. The second part of the hypothesis, we're testing concentration. So if the concentration of a reactant is increased, the speed of the reaction will, again, either increase, decrease, or not change. Pause the video now and add this into your notes. Procedure. And you may notice in the booklet, you were not given a procedure. Together as a class, I want us to come up with a procedure for testing the effect temperature has on the rate of reaction. So, what kind of experiment can we do to test the effect the temperature will have on the speed of reaction? How are we going to measure our results to create an accurate outcome? What will we have to keep the same each time we do the experiment so we know that the temperature was the only thing affecting how we decided to measure the speed of the reaction? I want you to pause the video, look at the materials available, and come up with a plan as a class. Then conduct the experiment to see if your hypothesis was correct. So please pause now and do the first experiment. Now for part 2. How does changing the concentration of a reactant affect speed of reaction? So what kind of experiment can we do to test the effect changing the concentration of one of the reactants will have on the speed of reaction? How are we going to measure our results to create an accurate outcome? What will we have to keep the same each time we do the experiment so we know that the change in concentration was the only thing affecting how we decided to measure the speed of reaction? Again, I want you to pause the video, look at the materials, and come up with a plan as a class, then conduct the experiment and see if your hypothesis was correct. So please pause the video now. In your booklet, there is a space that says dependent variable. I want you to identify what the dependent variables are, or variable is, in the experiment that you just conducted. But what is a dependent variable? The dependent variable is the variable being tested and measured in an experiment. In the procedure we developed together as a class, what was our dependent variable? What did we measure to determine if temperature really did have an effect on the rate of reaction? Please pause, discuss as a class, and then add what you come up with to your notes. Now, as a class, I want you to determine the independent variables. The independent variable is the variable the experimenter is in control of changing. This variable is assumed to have a direct effect on the dependent variable. What things did we purposely change to see how it affected the dependent variable? Pause now and as a class discuss and then add your answers to your notes. Controlled variables. These are the aspects of the procedure that stay the same throughout the experiment. Any change in a control variable could affect our outcome, so these are all the things we ensure are kept constant every time we conduct the experiment. The only difference between trials should be changes in the independent variable. Pause and discuss as a class what you did the same in every single trial so that you knew the only thing affecting your dependent variable was your independent variable which you had changed. And that's it. You're good to move on to the C14 assignment.